You've now seen how we can take an object and cut it up into little pieces of length, and then add up all those lengths to get the total object. And we can take an object that has area, we can cut it up into little pieces of area, take the length of each side of each piece, and by multiplying them together, we get the little area, and then adding up the whole thing to get the total area. We want to extend this to other geometries, and you'll see that we want to respect the geometry of the problem because it'll simplify the math. But the pattern is going to be the same. We're going to take it, cut it up into little lengths, multiply those lengths together to get an area, and then add up all our little areas. Let's look at a problem you already know the answer to. We want to find the area of a circle. You could do what we've done before. You could call our axes the y-axis and the x-axis and define some area that has some length dx and some other length dy, and we could add up our x's and our y's and get our total area, and this would be fine. There is an issue here though, and that is that my x is actually a function of my y. As I go along in y, my x is getting smaller or larger. And this, trying to force this circular geometry into a Cartesian or rectangular coordinate system, while doable, is not the easiest way to do it. So I'd like to show you, starting out, what is a slightly easier way of doing it by respecting the geometry of the problem. Before, when we tried to find the length of a circle, we looked at a little differential length that had some arc length, and we said, look, that arc length we knew depended on the radius I was at and the angle that that arc subtends, or that it is subtended by the angle. And when I worked it out, the geometry, it was the radius times that little differential angle. That was my arc length. So this time, now all I'm going to do is I'm going to take that's one length. What if I chop my area up into pieces that are little angles or little arc lengths, but with some thickness now? So the one side I already know, it's ds, and that is r d theta. And yes, as I go in, my r is going to change, but the length of my arc on any given side is still r for that distance, or for that piece, times the d theta for that piece. And now all I have to do is work out my other length. So I need this one, and I'm going to call that, since we're moving along the r direction, I'm going to call that dr. So when I work out my little differential area, I'm going to get that for any given piece, my differential area is just the length of one side times the length of the other side, or in other words, this is just going to be dr times r d theta. Or we might write it r dr d theta as my little differential area. And now I just add up all my areas. So if we write this, our total area as a sum of all of our areas, we're going to integrate this from of r dr d theta. Once again, you can see that all of this depends on r, and only this bit depends on theta. And what's more important is that for any given piece of theta, it's always at an r. It's not that, unlike the x and the y coordinates, my r doesn't depend on theta and my theta doesn't depend on r, so they're entirely separable. And I can rewrite this as I did before. I'm going to have two integrals, an r dr and an integral in theta. For the radial integral, I might say that this circle has a radius, big R. And so I'm going to integrate from 0 to big R. And of course, I want to integrate around a circle. So just as before you saw us, we're going to integrate for a whole circle that's 0 to 2 pi. My R integral ends up being 1/2 r squared, evaluated from 0 to r. And my theta integral is going to be theta, evaluated from 0 to 2 pi. And when I work that out, when I put those together, I'm going to get 1/2 r squared times 2 pi, or in other words, pi times r squared, which you should of course recognize as the area of a circle. So we found the area by cutting up our circle into little bits, trying to find out what the length of each side of those little bits were, respecting the geometry of the problem. And then multiplying those lengths together, we got our differential area, and just as before, we add up our area to get the total. Now I called that method hard mode because we had to go back to our basic idea of finding two lengths, multiplying them together to get our differential area. If our symmetry in our problem will allow it, we can actually do something and make the calculation easier. It's sort of pre-doing the integral by, instead of chopping this up into some little differential segment, we actually can instead cut it up into a little differential ring. So if I draw a ring here, and imagine that that were a circle, well, that circle would have, for a given radius, say the radius is r, well, we know what the length of a circle is. We already worked it out. So the length for this little piece, the one part of my length, is just going to be 2 pi times my radius. That's the length of this little differential piece. And now, if I increase that by giving it some thickness, so I find that I give it some thickness, a little differential piece of thickness, all the way around, so that the thickness of my line is now some dr, then I can get my area, my differential area, as my differential length times my thickness, or in other words, by 2 pi r dr. And you can already see what's happened. We've sort of pre-done the angle integral. The rest is all the same. We just take our differential area and add it up. So we take the integral of 2 pi r dr from 0 to our radius. And when we do that, of course, the 2 pi comes out. We have the integral from 0 to the radius of r dr, which is 1/2 r squared evaluated at the endpoints. Or in other words, this whole thing comes out to be, the 2's cancels with the 1/2, pi r squared, just the same as before. So sometimes the symmetry of the problem can allow us to break it up into different ways that might make some of the math easier, so we don't have to go back to the multiple integrals. Now we've shown you hard mode, where we cut the circle into little arcs of thickness, And I've shown you easy mode where we cut the circle into little circles, little rings of thickness. Let's show you very hard mode. Let's suppose you are just bound and determined. You say, hey, I'm just going to chop this into squares or rectangles, and I want to stick with x and y, and I must do it in Cartesian coordinates. Can you do it? The answer is yes, but it is hard. We're going to have to leverage what we know about a circle, that the equation of a circle is its radius squared equals its x coordinate squared plus its y coordinate squared. And we're going to have to make some choices. We can either integrate along x with our endpoints of our y changing as we go along, or we can integrate along y and have our x endpoints changing as we go along. I'm going to choose to integrate along y and let my x endpoints change. So let's work out what our endpoints then are for our integration. Our area is going to be simple. It's still dx dy. But my limits of my integral are what are going to be the hard part. So the limit of my integral in y, that's just, I'm going to go from minus r to r. Now I've got to figure out what my limits of x are, so I can take this equation for the circle and I solve it for x to find this point and this point on my circle. And if I do that, that's going to give me my limits. I take the square root of r squared minus y squared. On the positive x direction, I'm going to have the positive root. On the negative x direction, I'm going to have the negative root. So now I've got my limits, and I can plug that in to my integral, take the integral of dA. dA is, of course, dx dy, and I take my integral. But what do you notice? So this integral is just the integral of dx. And we know what that is going to be. The integral of dx is just going to be x. But my limits aren't independent of y, and so this is not separable. I'm going to have to integrate x first, and then that's going to give me a function in terms of y, and then I can integrate along y. So I do that, and in fact, actually, I said it was hard mode, but I'm still going to cheat. I'm going to notice the fact that this is a circle, and so if I get the area of 1/4 of the circle, I get the whole area. And so I'm just going to change my limits. That way I can ignore all of the negatives. The endpoints of my integrals become zeros, from 0 to r, and from 0 to square root r squared minus y squared. And it's nice because I can just deal with zeros, and zeros are easy. Now I plug that into my integral. I find the integral of dx. It's just square root r squared minus y squared dy from 0 to r. And at this point, I could look this up in a table, but I think it might be useful to show you the connection between this integral that we've got here in terms of x and y, and how that connects with our earlier polar integral. To show you this connection, I'm going to make a substitution for y. Now, how should I substitute for y? This takes some experience. This takes some artistry. Once you get some familiarity with solving integrals like this, you begin to see where the substitution and what substitution should be. This is called a u substitution, by the way. I'm going to let y equal r sine of u. It doesn't matter what u is, by the way. R sine of u. Then dy is just going to simply be r using my, this is the chain rule. So dy is r cosine of u, and then I have to take the derivative of u, which is du. So I've got now y and dy in terms of u. But I want to get my endpoints as well. What is when y equals r and y equals 0? So when, let's see, if I want y to equal 0, well, that's the same as saying if u is 0, because sine of 0 is 0. What if I want now y equals r? Well, I notice that means that I want this sine to equal 1, and that's going to happen when u equals pi over 2. So essentially, I've just defined u to be some angle from my x-axis, where when that angle is 0, I get y equals 0. And when that angle is pi over 2, I get y equals r. That's exactly like theta we had before, and so you can see where this connection is coming from. Now I make my substitutions. If I plug those in, I'm going to have under the radical where I had y squared, I'm going to now have r squared sine squared of u. And where I had dy, I'm going to have r cosine u to u. Now, I notice that there's an r in both terms under my radicals, so I can do a little bit of factoring. I can pull that out of the square root. I also have an r over here, and that's the radius. It's independent of u, so I can pull it out of my integral, and I get 4r squared. And now I have this integral of 1 minus sine squared u cosine u du. Now, I don't want to do that. So let's see if we can't simplify 1 minus u minus sine squared u. And I'm going to remember that sine squared of u plus cosine squared of u is 1. And so if I do that, I can simplify 1 minus sine squared u to be cosine squared u. And that's under the square root. So of course the square root of a square is going to be the thing itself. So I get cosine of u. Technically I get a plus cosine squared u or a minus cosine squared u. But since I'm in the first quadrant, I'm just going to use the positive root. And I can make that substitution now. And I get something that simplifies down nicely. We just get something that is cosine squared u du from 0 to pi over 2. And this is an integral we've seen before. We know what the answer is. We looked it up in the table before. So that's just u over 2 plus sine 2u over 4 evaluated from 0 to pi over 2. Now, when I plug 0 into any of these, it comes out as 0. When I plug pi over 2 into sine 2u, I'm going to get sine of pi, which is 0. And so the only thing left is u over 2. So I go ahead and plug it in. I'm going to get 4r squared times pi over 4, which ends up being pi r squared. So to find our result in Cartesian coordinates, we ended up having to turn it back into an integral along polar coordinates anyway. So often you just want to start with leveraging the symmetry of the problem and letting the symmetry of the problem determine the way you're going to do your integral. But other than that, the way we find an area in any sort of cylindrical geometry or circular geometry or spherical geometry is going to be the same as we've done for Cartesian. We just let now our symmetry of our problem determine how we're going to break up our shape.